So, good afternoon to all. Sir, how much time I will be getting? So, I think we lost some time. I know,
you get 20 minutes, ma'am. You can go ahead.
Okay, all right.
Okay.
All right. So, the theme is FEM modeling to ascertain movements of rainfall soil structures. So, I really felt to push for more research as well as the uh, the inclusion in the different codes and guidelines about the serviceability criteria of rainfall soil structure. The reason is that we are seeing a lot of issues in rainfall soil structures nowadays. We know that rainfall soil structures are having a lot of advantages. It has become very popular in India and different our neighboring countries also. In fact, the way India is constructing rainfall soil structures now, that is really looked by the global countries. As I am working in that, I know that how the colleagues, my global colleagues, are looking at India as a country where really a boom is happening. The lakhs and lakhs of square meter of fascia area reinforced soil structures are getting constructed. Again, we are even the retaining structures, very special retaining structures, we are now constructing as reinforced soil. So it's important to understand that are we considering all the different aspects of in the design stage itself or in the planning stage itself, or are we going in a reactive mode? So when we are looking at the present, the standards, the guidelines, even the national and even international, for the design and analysis, the basically the limit equilibrium methods. LE method is the most popular and the practiced method. LRFD method is getting introduced. And for allowable stress method for like embankments on soft soil, those type of applications, it is getting introduced. And what are the various checks? So everywhere, the external stability checks are there, like sliding, limiting eccentricity, overturning, bearing capacity checks, like any retaining walls. For reinforced soil wall also, the dimensioning, like base width, any optimization when we are working out the total the geometry. So that also governed by the external stability. When it is coming to the type of reinforcement, the tension element, the geogrid or steel strip or steel mesh, the internal stability checks governs the rupture or the pullout. And the internal slips, the local slips, all these will govern the selection of the tension elements. Its strength, it will be governed by the internal stability checks. The spacing, it will be governed by internal stability checks. Global stability analysis also is given enough importance, especially when we are placing a reinforced soil structure in a hill infrastructure. Definitely it is very much important, the global stability, and all these are given due importance. And we can see that nowadays a lot of specialized consultants are there, the specialist constructors are there. So the skill is there, but the gaps are also there. That is where we are hearing a lot of issues where alignment problems are there. If the fascia is of concrete panel, it is it's coming out. If it is with some other fascia, if it is a vegetated fascia or a given fascia, some movements are observed, some bulging out is observed. So how we can control this? So there should be a lot of causes are there, and something like the providing drainage or the compaction, making it more stringent, the criterias, All these we are discussing, but according to me, from the planning stage and the design stage itself, if the regulations are controlling, especially the codal standards are controlling, then definitely that will really bring a change in the overall picture. So one of the main gap is the serviceability criteria is not given enough importance, and how we can bring to it. So one way is the structures which are getting constructed, the movements during the construction as well as the post-construction stage, monitor it. The monitoring can be by observational methods or the instrumentation. And in the IGC 2018, my keynote is about the instrumentation method. So the same structure, I am taking it here for advocating the numerical method in the design stage. So the complex reinforced soil structures will be definitely requiring analysis and design based on the movement potential. So examples of such cases, tall reinforced soil structures, maybe the reinforced soil structures more than 15 meters. The reinforced soil structures with the space limitations, where a superstructure is rigid structure and the reinforced soil structure is a complete flexible structure. Then very poor ground conditions, that also can cause, of course, the vertical settlement, the lateral extrusion. So all these can definitely require special attention. So it is required to, it is not replacing the existing method. The existing methods are to be there, but it is required to supplement the design calculations recommended by the standards, the national or international standards, with more advanced techniques. And definitely the numerical methods, the FEM, can be a added advantage, and it need to be incorporated. So a structure which I want to present, this is a structure which is in Himalayan state, Uttarakhand. The same structure I presented in for IGC Bangalore, where the instrumentation was my focus. So here I am talking about the numerical method, where we have tried to find out how much this structure may move if we are constructing by virtue of its geometry, by virtue of its geological characteristics, as well as the type of fill which is being used as the structural fill, as well as the fascia. So definitely the entire actual conditions in the field, as well as even the reinforced soil structure, that was difficult to represent in the FEM. But the main features like the type of the soil, the type of the fascia, the type of reinforcement, that was represented in the FEM. So let us look at this structure. So this structure, the one of the main feature which is making it more prone to movement is its geometry itself. It is a 25-meter high structure. Okay, and this is in a extremely complex environment. It is in a Himalayan condition where a lot of subsurface flows are there. Geological condition is complex. Then there is the seismicity is between zone 4 and zone 5. And now coming to the reinforced soil structure, that itself is a composite soil reinforcement system, where the main reinforcement is a polymeric element. It is a polymeric element, two types of geogrids, which is having the bottom blocks are having the strength some 700 kilonewton per meter, and the top blocks which are having the main reinforcement 500 kilonewton per meter as the short-term strength. Then the fascia, the lower blocks, those are having the Gabian fascia, and upper blocks are having the vegetated fascia. So both Gabian fascia and the vegetated fascia is made of woven steel wire mesh elements, which are having some elongation and some strain absorbing characteristics. Then there is a Gaussian wall, a pure gravity Gaussian wall is placed at the top the block, reinforced soil block, and the overall structure will be, even if some beams are provided, that will be acting as a reinforced soil slope, we can say, ignoring the top portion is a Gaussian gravity wall. So this is the structure. And of course, the short-term strength, whatever I mentioned here, that need to be reduced as per the practice, as per BS 8006, which is the most popular code, or the IRC SP 102. We have to apply the different reduction factors, like reduction factors against creep, reduction factors against insulation damage, reduction factors against the chemical and biological damage. So all these material factors, as per the different manufacturers' certified data, that need to be applied. For this particular project, this data has come out to be together, all the reduction factors come out to be almost 1.65. But that is not our topic. Our topic is the movements, whether this structure, whether this will be having movements which will be exceeding the limits which that the entire infrastructure can take. The infrastructure, what is coming here, it is a road, and definitely a movement beyond, say 500 mm, that may be creating the problem in the road. So that we will talk about that 500 mm later. So before that, for the numerical modeling, definitely for a FEA modeling, we know the initial development of conceptual model, that may be the step one. Then boundary need to be defined. Then geometry, the soil properties, reinforcement and the fascia, all these properties need to be defined. The material modeling and parameters that need to be as precise as possible, practically possible. Then mesh generation, the stage construction, especially when we need to monitor the different behavior during the construction and post-construction. So these are the main steps. And the most important step is the validation of the results also. So the properties for the weathered rock, the existing, the strata that is of weathered rock, over that there is an overburden also. So these two strata, which is the pre-construction time itself, that is existing. Definitely for the reinforced fill, the backfill, as well as the fascia Gaussian fill, those properties also need to be defined. So the saturated unit weight, unsaturated weight, angle of internal friction, these are all the normal data which is applicable for reinforced soil. Those are defined. Of course, cohesion also. Now, the Poisson's ratio and the elastic modulus, these are specifically required for the numerical modeling, and those need to be defined in a proper way, especially for the reinforced fill, the elastic modulus, the backfill. These two are very critical, because to find out the lateral deformation or the lateral movements, as well as the vertical settlements, the most influencing parameters will be the reinforced fill as well as the backfill. The fascia, of course, that also will be having the local deformations and local strains that will be influenced by the fascias, of course, the stiffness as well as the elastic modulus. So those need to be as much accurate as possible, that need to be represented. So now coming to the material model. The material model, the linear elastic material model was selected for both weathered rock and overburden strata. And for the backfill, structural fill and reinforced soil, Moore-Coulomb model was selected. And coming to the reinforcement, again, the stiffness of the reinforcement is definitely a factor, especially when we are going for tall reinforced soil structures. So we cannot go for the strength criteria only. So in this case, two geogrids which were selected as the main reinforcement. The 700 kilonewton per meter geogrid that is having a stiffness of 7,937 kilonewton per meter. And for the 500 kilonewton per meter strength, the geogrid that was having 5,284, that is the axial stiffness value. Whereas for the facing, the Gaussian mesh, the value is 300 only. The reinforcement type that is defined as elastoplastic. And for the mesh generation, medium element distribution with the 15 ordered elements, it was triaxial elements, and it was in Plaxis 2D was used as the FEM software. So after generating the mesh, the entire reinforced soil structure, including foundation and the overburden strata, were divided into 27 stages. So it was very important to understand that how the each construction stage, how it is behaving, especially because of the subsurface flows, as well as the different climatic condition what is existing in this area. So all these structural elements and geometry changes, backfilling, excavation, and the placement of the structural elements layer by layer, it was not activated during the first stage of construction. And then by analyzing the worst state, that's the construction step, that is in the just the first few layers are being placed, whereas the entire surcharge, entire subsurface flows, everything is active there. That time itself, how much movements can be happened, that was being assessed. So then the remaining 26 stages were generated as per the staged construction. And after defining these 27 stages, the plastic analysis was performed in order to get the deformation of the reinforced soil structure. So for the validation of whatever the values we got from the FEM analysis, the maximum values what we got from the FEM analysis was 368 mm, which is a significant value, 36 centimeter, the top can move. So to validate it, the theoretically a empirical curve which is given by FHWA, that was being taken, and as per that, the delta R from this graph for the different L by H value, that was coming as 1.4, and this, using this, we are getting a delta max of, or the maximum possible deformation that can happen is 466 mm. So the from the FEM analysis, whatever we got, that was less than this limiting value what is predicted using the empirical curve which is given in FHWA NHI 10024. So this validation is also quite important. So now I'm going to the second case. This is a case in South India, a coastal area. An embankment has to be constructed in a very slushy soil. And the existing road embankment, it is almost 2 meter height, and the foundation soil layers are having very poor soil bearing capacity. And definitely excessive elastic and consolidation settlement, there is enough potential is there. And the biggest challenge will be to arrive at a stability against rotational movement, as well as to prevent the lateral extrusion of the clay underlying the embankment soil. So the solution which was given for this problem was a basal reinforcement with a high strength geogrid, which is having good stiffness also. But it was important to understand that because the soft clay was extending up to 8 meter to 10 meter, And this soft clay is prone to the vertical settlement as well as the lateral movements. Lateral extrusion can be a possibility.
Madam,
So to understand,
sorry to stop here. So you have another couple of minutes you can take and wind up.
right.
Okay.
So it's only 2 or 3 slides, so I can finish. So the stress distribution as well as the strain and deformation control, apart from the stress distribution, strain and deformation control, how we can find out. So the FEM was being employed here. And these are some of the how the properties are defined. Definitely the density, the angle of internal friction, cohesion, then elastic modulus, the Poisson's ratio, permeability, all these are defined using the model. And the reinforcement properties, those are also defined. Here, the FEM was very well. In the previous case, I have specifically told that the geogrid types are, it is already defined. And after that, we have applied FEM. Whereas here, FEM is employed to find out the most suitable geogrid for the basal reinforcement. So here what we are seeing is the different types of reinforcement, different types of grades, like grade 1, 2, 3, 4, 5, 6. So grade 1 corresponds to 100 kilonewton per meter, 2, 200, 3, 300, 4, 400, like that. So correspondingly, the vertical settlement, we can see that, we can see that the vertical settlement is getting reduced when the strength is getting increased. So the again, the lateral displacement maximum is there when we are using only 100 kilonewton per meter, but then it is getting reduced. Okay. And this is for a embankment, it is for a road embankment. IRC 75 is permitting up to 300 mm. So even with the grade 1 also, we are getting, it is within limits. Okay. Then coming to the bearing capacity check, again, we need to know that what is happening within the clay at different layers. So if we are seeing that y is equal to 0, y is equal to 0 is at the junction between the soft clay and the embankment. And at different depths, like 0.25 y, 0.5 y, and up to y, the pattern of the stress development that was able to be taken from the FEM analysis. And we can see that for above 0.5 y, it is really quite high. And the bearing capacity of the soil, that is almost 60 kilonewton per meter. So definitely this is really showing that this is requiring not only the basal reinforcement, some deep foundation techniques also is to be adopted. So the conclusion is that the numerical modeling is a very useful technique to study the performance and behavior of reinforced soil structure, whether it is a reinforced soil slope or a wall or a basal reinforced embankment. And nowadays, recent advances in computer processing technology and the availability of wide variety of softwares that is there. And it should be noted that before adopting the results of any numerical model, proper validation and confirmations of the model with the non-case study results on physical model test or classical analysis results is essential. And this presentation here, the procedure of numerical modeling of reinforced soil structure through 2 live project illustrations that is presented. One is a tall, steep reinforced soil structure in Himalayan zone, and the other is a basal reinforced embankment on soft soil in South India. That's it. Thank you.
Yeah, thank you, ma'am. Thank you. It's a wonderful lecture covering 2 aspects of the reinforced soil wall. And Dr. Singh, can we take few questions if they have? I don't know how to take questions from other people apart from those who are presenting here.
I think in the chat box there is no question.
Okay. I think in the chat box, I guess only these 9 people who are here, including me and you, can only post. I don't know about questions from others.
Yeah.
Anybody here? You have any questions on the presentation?
Yeah.
Okay, ma'am, I have a couple of questions for you.
Yeah.
So one thing is because the first one, especially the first one, is very, very important because you are constructing constructed RE wall. But whether Macceferri being a very, very huge organization, bringing geosynthetic solutions to India, whether there is any monitoring, the instrumentation using monitoring was done in this particular case, because see, whatever you showed, I don't know whether that can be called as a validation of your numerical model, because see, you are only comparing with FHW report, where the lateral movements, you compared your model results with that. But whether there are any in any project, whether this project or other projects, whether you are doing any instrumentation to see whether things are really going well.
Yeah, sir, that was what I mentioned, that I have presented in IGC, in fact, in 2018. It is about the instrumentation of the same project. That is why I didn't mention it in this presentation. So the extensive instrumentation is happening. The complete structure during the construction as well as post construction, the strain gauges, the pressure cells, inclinometers, deflectometers, it is completely the monitoring is going on. But contrary to our calculations, till the construction ended and even the first year, the complete data that was showing that it is the movements happened is only quite negligible. It's like few, I will say less than a millimeter. That much only the movements happened. Maybe because of one reason is, as it was a 25-meter high structure, the construction was very careful. Okay, layer by layer with the utmost carefulness was there. Second is whatever we are calculating, as you rightly said, that it is a very empirical equation only what FHW is giving. In fact, FHW and other codes have to give more more equations, because that is only a aspect ratio only is being taken, L by the height by L only. Whereas in this case, the stiffness plays a part. We are talking it as a extensible reinforcement and calculating the movement using that FHW equation, and it has come out to be 466 mm. But in fact, the geogrid which we are using, that is a stiffer element. So because of that stiffness, it's definitely having high resistance. Third is the factor of safety which is being used. It is designed for the high seismic condition, zone 5, and that is never getting mobilized in the static condition unless those type of dynamic movements are happening. So that is the
Fine. So madam, my last question, very quick question. So, madam, when you construct RE wall, so nowadays you clearly mentioned that there are many walls which are undergoing distress. Maybe there is a bulging, there is outward movement. Now, can you tell me whether from vertical any outward movement is accepted or acceptable during the construction or post construction?
Yeah, sir, it depends on two major factors. One is what is the type of infrastructure it is supporting. If you are placing a rigid structure on the top of it, okay, then definitely that rigid structure, if that is not able to accommodate the movements, then definitely we have to restrict as per the criteria of the rigid structure. Okay, and a rigid pavement is going, it may get cracked. A construction is going on the top of it. Those type of structures are also happening. So there we have to limit as per the criteria that. But if it is like a embankment, a highway embankment, where a flexible pavement only you are keeping above this, so then I will take IRC 75. It is permitting up to 300 mm vertical settlement, and the lateral movement it is taking up to say as per the again the different situation, I will say as per the different situation, but it is again permitting something like 300 mm. Okay, and 25 mm per year it is means NSE allowing. So it depends on the different type of structures, but the limiting conditions are to be incorporated at the time of design. Otherwise, these structures are flexible; they are supposed to move, and the many times it will come as a disastrous results if it is not taken care.
Thank you very much, ma'am. Thank you.
Thank you.
So, Dr. AP Singh, can you say a few words about this, and then we can proceed?
Yeah, very realistic analysis and calculation of the actual projects you have done, ma'am, and appreciable work. And one point I want to have your idea, okay, allowable settlement or your calculated settlement or deflection is what we are getting, and in actual we are not getting even a fraction of it, because in actual condition the worst condition is not simulated at the site. So do we need more optimization regarding this deflection and settlement criteria and calculation, or leave it for that worst condition to take place?
No, see, as per me, we should not go for too much aggressive optimization, especially considering the importance of structures. That is where for the reinforced structures an importance factor also is there. Yeah. If it is a temporary construction, or if the settlement or movement is not affecting any life or anything, okay, fine, we can go for optimization. But where the structure is quite critical and it's any movement can cause disastrous results, definitely we have to design for the worst and critical conditions. And the monitoring, as Moti sir said, the monitoring is most important for such type of structures. Because anytime for in the Himalayan condition, anytime there can be a flash flood or a event can happen. The same which is happening in our coastal states. Many times the complete sinking of the roads after the construction, it happens. And it's like maintenance is happening every second year or third year, maintenance has to happen. Otherwise, for a lot of accidents, as well as very uncomfortable riding will be there. So this is so important, and we cannot dilute that, according to me.
Yeah. Okay.
Okay, thank you, ma'am. So wonderful lecture, and definitely you are always available for our further questions. And with this, we once again thank you for providing an excellent lecture.
Thanks to all for giving me the time, even if we ran out of the time, and for patient listening.